Tonight, we are going to talk about something that is happening to you right now, at this very moment, as you lie still in the dark. Something enormous, something silent, something that has been pulling at you, and at every star you have ever seen, and at every galaxy beyond those stars, for longer than the human mind can truly hold. You have never felt it, you have never heard it, and yet it is real, and it is relentless, and it is dragging our entire galaxy through the void at a speed that would make every human achievement feel like standing still. Here is what most people never realize. Our Milky Way, this vast island of 300 billion suns, is not drifting through space at random. It is being pulled, drawn, called towards something so massive, so distant, and so deeply hidden that for decades, astronomers could not even agree on whether it was real. They called it the Great Attractor, and the name alone should tell you everything. An object or a region or a concentration of mass so extraordinary that it bends the flow of hundreds of thousands of galaxies simultaneously, pulling them all slowly, irresistibly, in the same direction. In our direction, or rather, in the direction we are all already falling toward, together, whether we know it or not. The terrifying part is not the scale, though the scale alone is enough to make the mind go quiet. The terrifying part is the silence. No warning, no signal, no force you could ever measure with your hands or feel against your skin. Just a pull, ancient and patient, operating across 250 million light years of empty space, reshaping the destiny of everything that exists in our corner of the universe. And hidden behind a curtain of our own galaxy's dust and starlight, the source of that pull has been nearly impossible to see. Science only began to glimpse it in the last few decades, and the closer we look, the stranger and deeper the mystery becomes. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. By the end of tonight, you're going to understand exactly why the Great Attractor is one of the most profound and unsettling discoveries in the history of cosmology, what it means for our galaxy, for our world, and for the quiet fact that every atom in your body is at this moment falling through the dark towards something we still cannot fully explain. Now let us begin. Right now, as you breathe slowly in the dark, something is happening that no one ever told you about. Not because it is a secret exactly, but because it's so vast, so silent, and so far beyond the scale of ordinary human life that most people never pause long enough to let it settle in. Our galaxy is moving. Not drifting, not wandering, moving with purpose and direction, drawn by a force so immense that astronomers spent decades simply trying to confirm it was real, and the more you sit with that fact, the more extraordinary it becomes. Think about what it means to be still. You are lying down right now, or sitting quietly, and everything around you feels fixed and motionless. The walls of the room are where they were this morning. The stars outside, if you could see them through your ceiling, look exactly where they looked last night. We experience the universe as a stable, settled place, a backdrop, a context, something we exist inside of, without ever really questioning whether it too is in motion. But it is, everything is, and the scale of that motion is something that requires a certain kind of stillness to absorb properly. The Earth rotates on its axis at roughly 1,000 miles per hour at the equator. You cannot feel it, but it is happening constantly, spinning you through darkness and light every 24 hours. At the same time, the Earth is orbiting the Sun at about 67,000 miles per hour. That is already a number that stretches comprehension. 67,000 miles every single hour, and yet you feel nothing. No wind, no pressure, no sense of movement whatsoever. Because everything around you, the air, the ground, the oceans, is moving with you at exactly the same speed. And that is just the beginning. The Sun itself is not stationary. It is orbiting the center of the Milky Way galaxy, carrying the Earth and all the other planets with it at a speed of roughly 500,000 miles per hour. 500,000. Our entire solar system is sweeping through the galaxy in a vast arc that takes approximately 225 million years to complete. The last time our Sun was in the position it currently occupies relative to the galactic center, the dominant life on Earth was early dinosaurs. Before that, trilobites. Before that, barely anything at all. The scale of cosmic time and cosmic motion is genuinely difficult to hold in the mind all at once. But try, because it matters for what comes next. Now here is where it gets truly astonishing. The Milky Way itself, this enormous galaxy containing somewhere between 200 and 400 billion stars, is also moving. Not just orbiting something. Moving through space as a whole, being carried along with hundreds of thousands of other galaxies in a vast river of matter flowing in a single direction. And at the destination of that river, or at least somewhere along its course, sits something that has no official name in the way planets and stars have names. Something that astronomers call, with a quiet kind of gravity, the Great Attractor, a region of space so densely packed with mass, both visible and invisible, that its gravitational influence reaches across hundreds of millions of light years and bends the trajectory of entire galaxy clusters as if they were leaves caught in a slow ancient current. Here is the thing most people do not realize. When you look up at the night sky, you are not looking at stillness. You are looking at motion, frozen by distance. The way a plane crossing the sky looks almost motionless when it is actually moving at 600 miles per hour. Every single point of light you have ever seen is moving. And almost all of them, at least in our cosmic neighborhood, are moving in the same direction, toward the same destination, toward the same invisible point in space, and we are among them, hurtling through the void at 1,400,000 miles per hour, carried along in that current without any sensation at all. Complete stillness on the surface, terrifying momentum beneath. Astronomers first began to notice the anomaly in the 1970s and 80s, when they started mapping the velocities of nearby galaxies and noticed something that did not fit the standard models. Galaxies were not simply moving apart from each other the way the expanding universe predicted. There was an extra component to their motion, a drift, a flow, a lean in a specific direction. Something was tugging at them. Something vast and mostly hidden, lurking behind the densest, dustiest part of our own galaxy's plane, screened from our telescopes by billions of stars and clouds of interstellar material. Whatever was pulling them could not be seen directly, but its gravitational fingerprints were unmistakable. That discovery changed cosmology. Not immediately, and not without controversy. For years, scientists debated whether the anomaly was real or whether it was an artifact of incomplete data. But as the maps grew more detailed and the measurements more precise, the conclusion became harder to deny. There is something out there, roughly 250 million light-years away in the direction of the constellation Centaurus, that is massive enough to exert a gravitational influence on our entire local universe. Not on individual stars, not on single galaxies, but on superclusters, on vast sheets of matter stretching hundreds of millions of light-years across. Whatever it is pulling on all of it simultaneously. And this is where the story becomes both beautiful and quietly terrifying. Because the Great Attractor is not some distant abstraction that lives only in scientific papers and university lectures. It is the reason our galaxy is moving the way it is moving tonight. It is the invisible hand shaping the trajectory of our entire cosmic neighborhood across billions of years. And yet most people on Earth will live their entire lives without ever hearing its name, let alone understanding what it means. You, lying quietly in the dark right now, are one of the few. You are part of the small and curious fraction of humanity that pauses long enough to look up at the scale of things and ask the question that matters most. What is actually out there, and why is everything falling toward it? We are going to spend the rest of tonight answering that question together, one layer at a time, one discovery at a time, moving from the familiar to the extraordinary in the slow and patient way that the cosmos itself seems to prefer. There is no rush. The pull has been happening for billions of years, and it will continue long after tonight. So settle in. Let your breathing slow. Let the weight of what we are about to explore arrive gently, the way starlight does, travelling an unimaginable distance and landing softly. There is a particular kind of discovery in science that does not arrive with a single dramatic moment. No explosion, no flash of light, no single night where everything changes. Instead, it builds slowly, like pressure gathering behind a closed door, until one day someone pushes and the whole world on the other side turns out to be completely different from what anyone expected. The discovery of the Great Attractor was exactly that kind of moment. It did not happen in a single evening. It happened across years, across continents, across arguments and recalculations and sleepless nights in observatories, until a small group of astronomers found themselves staring at data that quietly refused to make sense. To understand what they found, you need to understand what the universe was supposed to be doing. By the 1970s, the scientific consensus was built on a foundation laid by Edwin Hubble decades earlier. Hubble had shown in the 1920s that the universe is expanding. Galaxies are moving away from each other, carried apart by the stretching of space itself, the way dots on the surface of an inflating balloon move apart without any of them being the centre of the expansion. This was one of the most profound discoveries in human history, and it held beautifully. Measure the velocity of a distant galaxy, and you would find it moving away from us at a speed proportional to its distance. The farther away it was, the faster it was receding, elegant, consistent, seemingly complete. But in the late 1970s, a group of researchers began doing something that sounds straightforward, but was technically grueling. They started measuring the velocities of hundreds of galaxies, not just their recession speed due to the expansion of the universe, but their actual peculiar velocities, the component of their motion that could not be explained by expansion alone. If the universe were perfectly uniform, these peculiar velocities would be small and essentially random, each galaxy nudged slightly by its immediate neighbours, but with no large-scale pattern. What they found instead was something that made the numbers on their pages feel almost threatening. The galaxies were not moving randomly, they were flowing together in one direction. The team that made this finding most definitively became known informally as the Seven Samurai, a group of 7 astronomers, including David Burstein, Roger Davies, Alan Dressler, Sandra Faber, Donald Lynden Bell, Roberto Turlevich, and Gary Wegner. In 1988, they published results showing that our own galaxy and hundreds of other galaxies across a vast region of space were all moving toward a specific point in the sky, at velocities far too large to be explained by any known gravitational source. They were being pulled. Something enormous, something they could not see, was drawing them all in the same direction. The name that emerged for this invisible source was immediate and intuitive: the Great Attractor. And just saying it out loud carried a weight that more technical terminology never quite could. Here is the thing most people do not realize about that discovery. The astronomers were not just finding that something was out there, pulling on distant galaxies. They were finding that our galaxy, the Milky Way, was caught in the same flow. We were not observers watching other galaxies get pulled towards something far away. We were participants. We were in the current. The entire local group, the cluster of galaxies that includes the Milky Way and Andromeda, and dozens of smaller companions, was drifting toward the same point, swept along in the same river of gravitational influence as hundreds of thousands of other galaxies spread across a region of space spanning more than 500 million light-years. The discovery was not about something out there. It was about us. The immediate problem was that no one could see it. The direction of the pull toward the constellation Centaurus in the southern sky happened to align almost perfectly with the plane of the Milky Way, the dense band of stars, gas and dust that stretches across the sky and marks the disk of our own galaxy. This region, known to astronomers as the zone of avoidance, blocks an enormous portion of the sky from optical telescopes. Starlight cannot penetrate it cleanly. Signals are absorbed, scattered, and distorted by the billions of intervening stars and clouds of interstellar material. The universe, almost cruelly, had hidden the source of one of its most dramatic gravitational effects behind the thickest curtain it had available. The Great Attractor was pulling everything toward it from behind a wall that our best instruments could barely see through. This produced years of genuine scientific controversy. Some researchers accepted the evidence of the peculiar velocity flows and concluded that something massive must be hiding behind the zone of avoidance. Others argued that the data was incomplete, that the measurements were biased by the difficulty of observing through such a cluttered region of sky, that the apparent flow might vanish once better observations were available. The debate was not merely academic. It went to the heart of how the large-scale structure of the universe was supposed to work. If the Great Attractor was real and as massive as the velocity data suggested, it would require revisions to cosmological models. It would mean the universe was lumpier, more structured, more gravitationally complex than the prevailing theories comfortably allowed. Gradually, painstakingly, using radio waves and infrared light that could penetrate the dust where visible light could not, astronomers began to peer behind the curtain. What they found confirmed the basic reality of the anomaly, but made the picture more complicated rather than simpler. There were galaxy clusters back there, dense concentrations of matter, and behind those, hints of something even larger, a vast supercluster of galaxies that dwarfed anything in the immediate vicinity. Each new instrument, each new survey, each new technique peeled back another layer and revealed not resolution, but depth. The mystery did not shrink as the data improved, it grew. What makes this chapter of scientific history so quietly remarkable is the emotional texture of it. These were human beings, working with instruments that were primitive by today's standards, trying to measure the motion of objects billions of light years away, often arguing intensely with one another about interpretations, facing skepticism from their peers and yet, gradually, collaboratively, arriving at a truth that no single one of them could have reached alone. The universe had been keeping a secret, a large one, and it took decades of patient, careful, sometimes contentious work to begin to understand what that secret actually was. Tonight, we are the beneficiaries of that work. We get to inherit the discovery without the struggle and hold it quietly in the dark, and let it do what all great cosmological truths eventually do. Make the ordinary world feel impossibly small and impossibly precious all at once. Before we can truly feel the weight of what is pulling us, we need to stop and sit with what is being pulled. Because the word galaxy gets used so casually in documentaries and science articles and late-night conversations that it has lost some of its power to astonish. We say it the way we say ocean or mountain, as if it is simply a large version of something familiar. But a galaxy is not a large version of anything familiar. It is a category of object so far outside ordinary human experience that the only honest response, when you really let the numbers land, is a kind of reverent silence. The Milky Way is our galaxy. It is the structure of stars and gas and dust and dark matter that contains our sun, our solar system, and every human being who has ever lived. From the outside, if you could somehow position yourself far enough away to see it whole, it would look like a flattened spiral, a slowly rotating disk with long curved arms of star-forming material winding outward from a dense central bulge. It is beautiful, in the way that only things of genuine enormity can be beautiful, the kind of beauty that takes time to arrive, because the mind needs a moment to adjust to the scale before the emotion can follow. Now, how big is it? The Milky Way is approximately 100,000 light-years across. 1 light-year is the distance light travels in a single year, moving at 186,000 miles per second. In 1 year, light covers roughly 5.9 trillion miles. So 100,000 light-years is 5.9 trillion miles multiplied by 100,000. That number has so many digits that writing it out becomes almost meaningless. What matters is the feeling of it. If you could somehow board a spacecraft capable of travelling at the speed of light and you pointed it directly across the diameter of our galaxy, you would still be travelling for 100,000 years before you reach the other side. 100,000 years ago, modern humans had only just begun to spread across the planet. Every civilization, every language, every war and poem and discovery that has ever happened on Earth would fit inside the travel time of that crossing. And yet the Milky Way is not considered a particularly large galaxy. It sits somewhere in the middle range. There are galaxies that dwarf it utterly. The giant elliptical galaxy IC 1101, for instance, stretches across more than 6 million light-years. If you placed it where the Milky Way is, it would swallow our galaxy and dozens of its neighbours without noticing. The universe does not deal in modest scales. Everything in it tends toward the extreme, and our galaxy, vast as it is by any human measure, is a relatively average island in an ocean of such islands. Within the Milky Way, there are somewhere between 200 and 400 billion stars. The uncertainty in that number is itself staggering. We cannot count them individually, the way you might count objects on a table. We estimate based on the galaxy's mass and the typical distribution of stellar types. And even our best estimates carry a range of hundreds of billions. Each of those stars is a sun. Some are dimmer than ours, and some are unimaginably brighter. Some are ancient, nearly as old as the universe itself, carrying in their spectra the chemical fingerprints of a cosmos that was still young. Some are newborn, still wrapped in the glowing clouds of gas and dust from which they condensed. The galaxy is not a static collection. It is a living system, constantly forming new stars, occasionally destroying old ones, cycling material through generations across billions of years. And around many of those stars, planets, we have now confirmed the existence of thousands of worlds beyond our solar system, and the statistical inference from those discoveries is that planets are the rule rather than the exception. Most stars likely host at least one, which means the Milky Way probably contains hundreds of billions of worlds, rocky ones and gaseous ones, and icy ones, and ones we have no category for yet. Worlds that orbit their stars in perpetual darkness, and worlds bathed in the light of multiple suns simultaneously. The sheer variety of what might exist within our galaxy alone is enough to make any single human life feel both cosmically small and cosmically significant, because we are here, somehow, among all of it, aware enough to wonder about the rest. At the very centre of the Milky Way sits a supermassive black hole called Sagittarius A star. It contains the mass of approximately 4 million of our suns compressed into a region of space smaller than our solar system. It is not actively feeding right now in any dramatic way, which is one reason our galaxy feels relatively quiet compared to some others, but it is there, always, an immense gravitational anchor around which the entire structure of the galaxy ultimately organises itself. The stars near the galactic centre orbit it at extraordinary speeds, some completing a full orbit in only a few years, whipping around an invisible point of infinite density in a cosmic dance that has been ongoing for billions of years. Our Sun is located about 26,000 light-years from the galactic centre, roughly halfway between the core and the outer edge, sitting in a relatively calm region between two of the galaxy's major spiral arms. This is not a dramatic address in galactic terms. We are not near the center, where the star density is highest and the radiation most intense. We are not at the outer edge, where the galaxy thins into scattered isolation. We are in the middle, in a kind of cosmic suburb, which turns out to be exactly the kind of location where stable planetary systems and long-lived stars, and eventually life-bearing worlds, have the space and time to develop without constant disruption. This is what is being pulled. This entire structure, 100,000 light-years across, 400 billion stars, hundreds of billions of worlds, one supermassive black hole at its heart, and somewhere on one of its outer arms, one small star with one small rocky planet carrying 8 billion people who mostly have no idea any of this is happening. All of it moving. All of it caught in the same gravitational current. All of it being drawn, slowly and irresistibly, towards something it cannot see, and we are only beginning to understand. When you hold that image clearly, the idea of the Great Attractor stops being an abstract cosmological concept and becomes something almost personal. Because whatever is pulling our galaxy is also pulling you, every atom of you, right now, in the quiet dark, falling forward through space toward an invisible destination at a speed no human being will ever feel. Imagine standing at the edge of a river at night. The water moves past you in the dark, carrying leaves and branches and everything that falls into its current, all of it flowing in the same direction, drawn by the same invisible pull of gravity toward the same distant sea. You cannot see the sea from where you stand. You cannot even see very far downstream, but the direction of the current is unmistakable, and everything in the water is going the same way, whether it wants to or not. This is, in its broad outlines, a reasonably accurate picture of the situation our galaxy finds itself in, except that instead of water, the medium is space itself, and instead of leaves, the objects being carried are entire galaxies, each containing hundreds of billions of stars, all flowing together through the void in one vast and ancient current. To understand the scale of that current, you need to understand where the Milky Way sits within the larger structure of the universe. Our galaxy is not alone. It belongs to a collection of galaxies called the Local Group, a gravitationally bound cluster of more than 50 galaxies spread across a region of space roughly 10 million light-years in diameter. The Local Group's two largest members are the Milky Way and the Andromeda Galaxy, also known as Messier 31, which is actually slightly larger than our own galaxy and is, incidentally, on a slow collision course with the Milky Way that will unfold over the next 4 billion years or so. The other members of the Local Group are mostly smaller dwarf galaxies, scattered companions orbiting the two larger ones, like moons around planets. But the Local Group is itself embedded within something larger. Our cluster of galaxies is part of the Virgo supercluster, a vast collection of galaxy groups and clusters spread across a region approximately 110 million light-years across. The Virgo supercluster contains somewhere around 100 galaxy groups, including our own Local Group, and has a total mass equivalent to roughly 1,000 trillion times the mass of our Sun. For decades, astronomers considered the Virgo supercluster to be our cosmic home address, the largest gravitationally coherent structure we belong to. And then, in 2014, that picture changed dramatically. A team of researchers led by R. Brent Tully of the University of Hawaii published a landmark paper in the journal Nature that redrew the map of our cosmic neighborhood in a profound way. Using a comprehensive survey of galaxy velocities across a huge region of space, they identified a structure far larger than the Virgo supercluster, a gravitational basin so enormous that it reshaped the way cosmologists thought about large-scale structure entirely. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. And the name is apt because Laniakea is genuinely difficult to measure in any way that feels intuitively graspable. It spans approximately 500 million light-years across and contains the mass of 100 million billion suns. It includes about 100,000 galaxies, of which the Milky Way is precisely one. One galaxy out of 100,000, in a supercluster that is itself one of many scattered across the observable universe. The key insight that led to the discovery of Laniakea was a new way of mapping the cosmic flow. Instead of simply measuring where galaxies are, the researchers mapped where galaxies are going, tracing the velocity flows across the region to identify the gravitational watershed boundaries, the invisible dividing lines in space where matter on one side flows one way and matter on the other side flows another. What emerged from that mapping was a structure that looked remarkably like a river system viewed from above. Long filaments of galaxy motion flowing inward from the outer reaches toward a central basin, tributaries merging into larger currents, everything draining toward a single low point. And at the bottom of that gravitational basin, the region toward which all the flows within Laniakea ultimately converge, sits the Great Attractor. This is what makes the river metaphor so fitting. Laniakea is not just a collection of galaxies that happen to be near each other. It is a dynamic structure defined by motion, by the flow of matter through space toward a common gravitational center. The Milky Way is not simply located within Laniakea, the way a city is located within a country, as a static occupant of a fixed territory. It is located within Laniakea, the way a boat is located within a river current, actively moving, caught in the flow, being carried toward the attractor at the basin's heart. The geography and the motion are inseparable. Where we are is defined by where we are going, and the speed of that motion is not trivial. When astronomers subtract out the component of galactic motion due to the overall expansion of the universe, what remains is a peculiar velocity, a drift that cannot be explained by expansion alone and must therefore be caused by gravitational attraction. For the Milky Way, that peculiar velocity toward the Great Attractor is approximately 1,400,000 miles per hour. Across the 500 million light-years of Laniakea, this current of motion is not uniform. Galaxies closer to the attractor move faster, pulled more strongly by its gravity. Galaxies near the outer boundaries of the supercluster move more slowly, at the edge of the watershed where the pull is weakest. But across the entire structure, the direction is consistent. Everything is falling inward. Everything is part of the same river. Here is the thing most people do not realize when they first encounter this picture. The structure of Laniakea, the very shape of the cosmic river, is itself a clue to the nature of what is pulling it. Rivers on Earth take the shapes they do because of the landscape they flow through, the hills and valleys carved by geology over millions of years. The cosmic river of Laniakea takes the shape it does because of the gravitational landscape of the universe, sculpted by the distribution of matter and dark matter across billions of years of cosmic evolution. The attractor at the center of that river is not just a massive object sitting passively in space. It is the gravitational low point of a landscape that was laid down in the first moments after the Big Bang, when tiny fluctuations in the density of the infant universe were magnified by gravity over billions of years into the walls, filaments, and nodes that define the large-scale structure of everything we can observe. So when you lie quietly tonight and think about the river of galaxies, think of it this way. You're not simply on a planet orbiting a star inside a galaxy. You're a tiny particle in a current that has been flowing for billions of years, part of a river 100,000 galaxies wide, draining through 500 million light-years of space toward a destination that shapes the entire structure of your cosmic home. The current is gentle by any experiential measure. You will never feel it, but it is as real as the ground beneath you, and it has been carrying everything you know and everything you are toward that invisible horizon for longer than the Earth has existed. There is something almost poetic about the fact that the greatest gravitational mystery in our cosmic neighborhood has spent most of its existence hidden behind our own galaxy. Not hidden in deep space, not concealed behind some impenetrable barrier of physics, but obscured by the very structure we live inside. The way you might fail to see a mountain range because you're standing in the middle of a forest that blocks your view in every direction. The universe, it turns out, has a remarkable talent for hiding its most important secrets in plain sight, or rather, in the one direction where our instruments are least capable of seeing clearly. And for astronomers trying to understand what was pulling hundreds of thousands of galaxies across hundreds of millions of light years, that obstruction was not a minor inconvenience. It was a fundamental barrier that delayed the discovery of the Great Attractor by decades. To understand why, you need to picture what the Milky Way looks like from the inside. We live within the disk of our galaxy, embedded in one of its spiral arms, surrounded on all sides by stars and gas clouds and vast lanes of interstellar dust. When you look out along the plane of the galaxy, the direction that traces the flat disk of the Milky Way across the sky, you are looking through the densest, most cluttered region of our entire galactic neighborhood. Stars packed so closely together in our line of sight that their light blurs and blends. Gas clouds that absorb and scatter radiation. Dust particles, microscopic grains of carbon and silicate materials that block visible light almost completely across large swaths of the galactic plane. The result is a band of sky that optical telescopes simply cannot see through, not because there is nothing there, but because everything between us and the far side is in the way. Astronomers gave this region a name that manages to be both scientifically precise and quietly dramatic. They call it the Zone of Avoidance. It earned that name in the early days of galaxy surveys, when observers began to notice that galaxy catalogues had a peculiar gap running along the galactic plane, a band of sky where no external galaxies appeared to exist. For a while, some researchers wondered if this was a real feature of the universe, a region genuinely empty of galaxies for some physical reason. But the more likely explanation was simpler and more frustrating. The galaxies were there. We just could not see them. Our own galaxy was in the way, casting a shadow across our view of the cosmos in precisely the direction where some of the most important structures in our local universe turned out to be lurking. The Zone of Avoidance covers roughly 20% of the entire sky. That is not a narrow strip. It is a significant fraction of our total observable window onto the cosmos, a band roughly 10 to 20 degrees wide on either side of the galactic equator, where external galaxy counts drop to near zero in optical surveys. And the Great Attractor, that enormous concentration of mass pulling our galaxy and hundreds of thousands of its neighbours through space, sits almost perfectly centred within this zone. The direction of the pull, toward the constellation Centaurus in the southern sky, places the attractor squarely behind the thickest part of the galactic plane. It is as if the universe specifically arranged its most dramatic gravitational feature to be hidden behind the one screen we could not easily see through. Whether that is irony or just geometry depends on your philosophical disposition. For the astronomers of the 1970s and 80s who were trying to map the peculiar velocity flows and trace them back to their source, this was a source of genuine scientific anguish. They could measure the motion of galaxies all around the obscured region. They could see the flow pointing toward a specific location in the sky. They could calculate the approximate mass required to produce the velocities they were measuring. But they could not directly observe the thing causing it all because it was hiding behind a curtain of their own galaxy's material. It was like trying to find the source of a river by watching its tributaries flow together, tracing them upstream toward a point where the river disappeared into a dense fog, and being forced to infer what lay beyond that fog from the behaviour of the water you could see. The breakthrough came not from visible light but from other parts of the electromagnetic spectrum. Radio waves with their long wavelengths can penetrate interstellar dust far more effectively than visible light. Infrared radiation, which carries heat rather than visible photons, similarly cuts through dust that would completely block an optical telescope. Beginning in the 1990s and accelerating through the 2000s, astronomers began systematically surveying the zone of avoidance using radio and infrared instruments, slowly building a picture of what lay behind the curtain. What they found confirmed the basic reality of the attractor region, but revealed a landscape of complexity that made simple explanations impossible. There were galaxy clusters back there, dense concentrations of hundreds of galaxies bound together by gravity. There were filaments of matter connecting those clusters, and there were hints of something even larger and more massive lying further behind. One of the most significant surveys was the HIPAS survey, the H.I. Parkes All-Sky survey, which used a radio telescope in Australia to map hydrogen gas emissions across the entire southern sky, including the zone of avoidance. Hydrogen gas emits radio waves at a characteristic frequency, and those radio waves pass through interstellar dust with barely any absorption. By mapping the hydrogen, astronomers could identify galaxies that optical surveys had completely missed, entire galaxies hiding behind the galactic plane, revealed only by the radio whisper of their hydrogen content. The results were striking. The zone was not empty. It was full of galaxies exactly where the velocity flows predicted the attractor region should be, clustered and concentrated in ways that confirmed a massive gravitational source in that direction. But here is what makes the zone of avoidance more than just a technical obstacle in the history of astronomy. It is a reminder of something important about the nature of knowledge and discovery. We are always, in some sense, working around our own position in the universe. We see what our location allows us to see, and we are blind to what our location blocks from view. The zone of avoidance is the most literal version of that constraint, a region of sky rendered invisible by the simple fact that we live inside the galaxy whose disk creates the obstruction. We cannot step outside our galaxy to get a cleaner view, any more than you can step outside your own life to get a perfectly objective perspective on it. We work with the view we have, develop tools to peer around the obstructions, and slowly, patiently, build a picture of what is there even when we cannot see it directly. And the picture that has emerged, imperfect and still incomplete, is one of extraordinary drama. Behind the zone of avoidance, behind the curtain of dust and starlight that hid it from us for so long, something enormous waits, something that has been pulling on everything we know for billions of years, patient and invisible, drawing the river of galaxies toward itself across distances that make the mind go quiet. We have only begun to see it clearly in recent decades, and what we have seen has raised more questions than it has answered, which is, in the end, exactly what the best discoveries always do. We have spent time understanding the motion, the history of its discovery, and the curtain that hid it from view. Now we need to talk about the thing itself, the source, the attractor. And I want to be honest with you from the start of this part of the conversation, because honesty is more interesting than false confidence, and the truth here is genuinely remarkable. We do not fully know what the great attractor is. We know approximately where it is. We know roughly how much mass it must contain to produce the gravitational effects we can measure. We know what lies in that general direction when we peer through and around the zone of avoidance with our best instruments. But a clean, complete, settled picture of the great attractor does not yet exist. What exists is a growing body of evidence pointing towards something of extraordinary scale, partially revealed, and still deeply mysterious. Here is what we do know. The great attractor is not a single object, not a black hole or a star or even a single galaxy. It is a region, a concentration, a gravitational basin in space where an enormous amount of mass, both visible and invisible, has accumulated over billions of years of cosmic evolution. This region sits approximately 250 million light-years from Earth, in the direction of the constellations Centaurus and Norma in the southern sky. At that distance, the light we receive from the galaxies in that region left them 250 million years ago, when the dominant life on Earth was early reptiles in the Permian period, long before the first dinosaur ever walked the planet. We are, as always in astronomy, looking at the past. What the region looks like today is something we cannot directly observe. The mass required to produce the gravitational influence we measure is staggering. Estimates have varied over the decades as the data improved and the models were refined, but the general picture requires a concentration of mass equivalent to tens of thousands of galaxies, perhaps the equivalent of 10,000 trillion suns, gathered within a region of space spanning hundreds of millions of light-years. To put that in terms that might help it feel real, if you took every star in the Milky Way and multiplied them by 10,000, and then multiplied that by another billion, you would begin to approach the mass that astronomers infer must be present in the Great Attractor region to produce the velocities they observe. Numbers like these stop being informative in the conventional sense. They become something closer to emotional, a scale of existence that the human mind cannot truly hold, but can at least gesture toward. What lies in that direction when we look, using every instrument available to us, is a landscape of galaxy clusters and superclusters of extraordinary density. The most prominent visible structure in the attractor region is the Norma cluster, also known by its catalogue designation Abell 3627. The Norma cluster is one of the most massive galaxy clusters in our local universe, a dense ball of hundreds of galaxies bound together by gravity, surrounded by vast quantities of hot gas that glows in X-ray wavelengths. It sits almost exactly at the distance astronomers had predicted for the core of the Great Attractor, and for many years it was assumed to be the primary source of the gravitational pull. But as surveys improved and the picture deepened, it became clear that the Norma cluster, massive as it is, could not account for all of the motion being measured. Something else, something larger, was contributing to the pull from further away. Here is the thing most people do not realize when they first learn about the Great Attractor. The gravitational influence we feel is not coming from a single sharp point in space. Gravity does not work like a spotlight, with a clean beam and a clear source. It works like weather, diffuse, overlapping, with multiple systems influencing each other simultaneously across enormous distances. The pull our galaxy feels is the net result of gravitational contributions from the Norma cluster, from the larger structures behind it, from the filaments and walls of matter that connect those structures, and from the vast quantities of dark matter that pervade the entire region. Separating these contributions cleanly is enormously difficult, which is one reason the picture has taken decades to assemble and remains incomplete. What we can say with confidence is this: the Great Attractor region is one of the most gravitationally significant locations in our observable universe. It sits at the convergence point of Laniakea, the supercluster we belong to, which means it is quite literally the gravitational heart of our cosmic home. The flow of galaxies across 500 million light-years all drains toward this point, in the same way that a continent's river system all drains toward the sea. Every galaxy in Laniakea, including the Milky Way, including the Andromeda Galaxy, including all the dwarf galaxies scattered between them, is part of this flow. All of it moving, all of it falling, all of it drawn toward that same dense basin, 250 million light-years away, and yet, terrifyingly, we may never reach it. This is the part of the story that, when you let it settle, produces a particular kind of quiet vertigo. The universe is expanding. Space itself is stretching, carrying distant objects away from each other at speeds that increase with distance. At the scale of the Great Attractor, the expansion of the universe is already competing with the gravitational pull. The attractor is pulling us toward it at 1,400,000 miles per hour. But the expansion of space is simultaneously carrying the attractor away from us. And at that distance, the recession velocity due to expansion is already comparable to the infall velocity due to gravity. We are like a swimmer caught in a current, stroking toward a distant shore, while the water itself carries the shore away. Progress is uncertain. Arrival may be impossible. But the pull is real. The motion is real. And the object, or region, or concentration of mass that is causing all of it is real, even if our picture of it remains incomplete. That incompleteness is not a failure of science. It is an honest acknowledgement of where we are in the long process of understanding the universe, a process that has been underway for only a few centuries in a cosmos that has been evolving for 13.8 billion years. We are early in our investigation. The instruments are improving, the surveys are expanding, and each new generation of telescopes and detectors peels back another layer of the mystery, revealing not simplicity, but depth, not a single source but a landscape of staggering complexity. The Great Attractor is not a thing we have found and catalogued and understood. It is a thing we are still discovering, slowly and carefully, one measurement at a time, in the patient way that the universe seems to reward above all others. Science has a habit of revealing that what you thought was the answer was actually just the next layer of the question. You peel back one mystery and find another waiting beneath it, larger and stranger than the one before. The story of the Great Attractor is a perfect example of this. For years after astronomers had confirmed the reality of the gravitational flow and begun to peer behind the zone of avoidance with radio and infrared instruments, the leading candidate for the source of the pull was a single massive galaxy cluster, sitting almost precisely where the attractor was predicted to be. It was dense, it was enormous, and it was right on target. For a moment, it seemed like the mystery had found its answer, and then the data improved, and the answer turned out to be only the beginning. The Norma cluster, catalogued as Abell 3627, is one of the most massive concentrations of galaxies in our local universe. It sits approximately 220 million light-years away, in the direction of the constellation Norma in the southern sky, just inside the zone of avoidance, and only recently made accessible to detailed study through infrared and radio surveys. The cluster itself contains hundreds of galaxies packed into a relatively compact region of space, their individual motions frantic at the scale of thousands of miles per second as they orbit the cluster's common gravitational center. Surrounding those galaxies is a vast halo of superheated gas, plasma heated to tens of millions of degrees by the gravitational compression of the cluster, glowing brilliantly in X-ray wavelengths and confirming just how much mass is packed into that region. By any ordinary measure, the Norma cluster is a titanic structure, the kind of object that would dominate the gravitational landscape of any neighborhood it occupied. And yet, as astronomers refined their velocity measurements and compared them to what the Norma cluster alone could produce, a gap emerged. The peculiar velocities of galaxies across the Laniakea supercluster, including the motion of the Milky Way itself, were larger than what the Norma cluster's gravity could fully explain. Something else was contributing to the pull, something further away, something that could not be seen directly even with infrared instruments, because it lay even deeper behind the obscuring plane of the Milky Way, and also simply because it was further, its gravitational influence more diffuse but still measurable in the motions of nearby galaxies. The search for that something led astronomers deeper into the zone they had been trying to penetrate, and what they found there fundamentally changed the picture. The Shapley supercluster, named after the American astronomer Harlow Shapley, who first noted an unusual concentration of galaxies in that region in the 1930s, is one of the most massive structures in the observable universe within a few 100 million light-years of Earth. It lies approximately 650 million light-years away, considerably further than the Norma Cluster, in roughly the same general direction as the Great Attractor. The Shapley Supercluster contains dozens of galaxy clusters, thousands of individual galaxies, and a total mass that some estimates place at more than 10 million trillion times the mass of our Sun. It is, by any measure, a gravitational colossus, and it sits behind the Great Attractor region like a second, far more massive engine, driving part of the same cosmic flow. Here is the thing most people do not realize when they first encounter the relationship between the Norma Cluster and the Shapley Supercluster. Gravity does not care about distance the way human intuition does. We tend to think of distant objects as having less influence than nearby ones, and in a simple, two-body sense that is true. But when a distant object is massive enough, its gravitational reach can extend across hundreds of millions of light-years and still contribute meaningfully to the motion of everything in that region. The Shapley Supercluster is so massive that even at 650 million light-years, its gravitational fingerprints show up clearly in the peculiar velocity flows of galaxies in our neighbourhood. It is not the primary driver of our galaxy's motion, but it is a significant contributor, a deep bass note beneath the more prominent pull of the closer Norma Cluster and the broader Great Attractor region. This layered picture, with the Norma Cluster in the foreground and the Shapley Supercluster behind it, began to resolve some of the tension in the velocity data that had puzzled astronomers for years. The measured flows were too large for any single cluster to explain, but they were consistent with a combination of gravitational sources at different distances, all pulling in roughly the same direction. The Norma Cluster provides the more local, sharper component of the pull. The Shapley Supercluster adds a broader, deeper contribution from further away, and between and around them, the filaments and walls of the cosmic web carry additional mass that contributes its own gravitational influence to the overall flow. The Great Attractor, properly understood, is not a thing, it is a direction, a region of space where gravitational sources at multiple distances and scales all conspire to produce a net pull that no single one of them could generate alone. What makes the Shapley Supercluster particularly striking as an object in its own right, beyond its role in the Great Attractor story, is its sheer scale when you try to visualize it. The entire Laniakea Supercluster, our cosmic home spanning 500 million light-years and containing 100,000 galaxies, would fit inside the Shapley Supercluster with room to spare by some estimates. It is not the largest structure in the observable universe. The cosmic web contains features even more extended, walls and filaments spanning billions of light-years. But within our local cosmic neighbourhood, within the region we can map in reasonable detail, the Shapley Supercluster stands as one of the most impressive concentrations of matter that exists. It is, in a very real sense, the mountain range toward whose foothills our galaxy has been falling for billions of years, visible now only because our instruments have finally grown sensitive enough to detect it through the obscuring curtain of our own galaxy's plane. There is something philosophically interesting about the fact that the pull we experience comes not from one source but from many, layered across different distances, each contributing its own gravitational voice to the overall chorus. It means that the destiny of our galaxy is not determined by a single dominant object, but by the accumulated gravitational influence of an entire landscape of structures, some near and sharp, some distant and diffuse, all working together across cosmic timescales to shape the trajectory of everything we know. We are not falling toward a single point. We are falling through a gravitational terrain of extraordinary complexity, shaped by forces that were set in motion at the very beginning of the universe, and that will continue operating long after every star now burning has exhausted its fuel and gone dark. And there may be more layers still to find. Each improvement in our instruments, each new survey that peers more deeply behind the zone of avoidance, or maps the velocity flows across a wider region, has tended to reveal additional structure rather than simplify the picture. What looks like the answer from a distance becomes, on closer inspection, another set of questions. The Norma cluster pointed us toward the Shapley supercluster. The Shapley supercluster hints at even larger flows extending beyond the boundaries of Laniakea. The universe, it seems, is not in the habit of offering simple conclusions. It offers instead an endless succession of deeper views, each one more astonishing than the last, each one a reminder that the map is always smaller than the territory it tries to represent. Let us talk about speed. Not the speed of a car on a highway, or a plane crossing an ocean, or even a rocket leaving Earth's atmosphere. Those speeds are remarkable by human standards, and we rightly celebrate the engineering that produces them. But they are, in the context of what we are discussing tonight, so slow as to be almost indistinguishable from stillness. The speed at which our galaxy is moving toward the Great Attractor belongs to a different category entirely, a category where the numbers are so large that ordinary language begins to fail, and the only honest thing to do is sit with the failure for a moment and let it point towards something true about the scale of the universe we inhabit. Our galaxy, the Milky Way, is moving toward the Great Attractor at approximately 1,400,000 miles per hour. Say that slowly. 1,400,000 miles every hour. The fastest human-made object ever launched, the Parker Solar Probe, reached speeds of around 430,000 miles per hour at its closest approach to the Sun, making it the fastest thing humanity has ever built. Our galaxy is moving at more than 3 times that speed, and it has been doing so continuously, not for a single close pass around a star, but for billions of years. That motion is not a sprint, it is a constant, relentless drift through the cosmos, ancient and patient, and utterly beyond any scale of human engineering. To make the number feel a little more real, consider this. 1,400,000 miles per hour means that in a single second, the Milky Way moves roughly 390 miles toward the Great Attractor. In the time it takes you to draw one slow breath, our galaxy has travelled the equivalent of the distance from New York to Montreal. In a single minute, it has moved more than 23,000 miles, nearly the circumference of the entire Earth. In an hour, it has covered a distance greater than the average gap between the Earth and the Moon, multiplied by almost 6. These are numbers that feel large at first, and then, when you place them against the actual distance to the Great Attractor, reveal themselves to be almost heartbreakingly small. 250 million light-years. That is the approximate distance to the core of the Great Attractor region. 1 light-year is roughly 5.9 trillion miles. 250 million light-years is therefore a number so large that writing it out in miles would require more digits than this entire script contains. At our current speed of 1,400,000 miles per hour, travelling continuously without stopping or slowing, it would take our galaxy approximately 1 trillion years to cover that distance. 1 trillion years. The current age of the universe is approximately 13.8 billion years. A trillion years is more than 70 times the current age of the entire universe. We have been falling toward the Great Attractor since long before Earth existed, and at our current speed we would not arrive for a duration of time so vast it makes the current age of the cosmos look like an afternoon. And here is the terrifying part. You feel none of it, not a whisper, not the faintest sensation of motion. You are lying still or sitting quietly, and nothing in your physical experience gives any indication that you are aboard a galaxy moving at 1,400,000 miles per hour through the void. This is not because the motion is too slow to matter. It is because motion at cosmic scales is only perceptible through its effects on other things, through the Doppler shift of light, through the gravitational distortions in spacetime, through the careful measurement of galaxy velocities over years of patient observation. Your body has no sensor for galactic drift. Evolution never needed to build one. The motion exists in a register of reality that your nervous system was never designed to detect. Here is the thing most people do not realize about the way we measure this speed. When astronomers say our galaxy is moving at 1,400,000 miles per hour toward the Great Attractor, they are measuring what is called our peculiar velocity, the component of our motion that cannot be explained by the general expansion of the universe. The universe is expanding, carrying all galaxies apart from each other, and that expansion contributes its own component to the apparent motion of any galaxy we observe. To find the peculiar velocity, astronomers must carefully subtract the expansion component from the total observed motion, leaving only the part caused by gravitational attraction. The fact that this is technically possible at all, that we can disentangle the motion caused by gravity from the motion caused by cosmic expansion across distances of hundreds of millions of light years, is itself a remarkable testament to the precision of modern astronomy. Think about what it means that hundreds of thousands of galaxies are all sharing a version of this motion. Not identical speeds, because each galaxy sits at a different position in the gravitational landscape and feels the pull with different intensity, but all moving in the same general direction, all drifting toward the same basin, all caught in the same river. The total kinetic energy represented by that collective motion is genuinely incomprehensible. Hundreds of thousands of galaxies, each containing hundreds of billions of stars, each star with whatever planets and moons and debris orbit it. All of that mass moving at speeds measured in hundreds of thousands of miles per hour, all flowing in the same direction across 500 million light-years of space. The universe is, in this sense, not a static stage on which events occur. It is itself an event, an ongoing, dynamic, structured flow of matter through space on scales that make every human drama feel like a footnote. And yet the footnote matters. This is the paradox that the scale of the universe always eventually delivers. You are part of this motion. Every atom in your body, every thought moving through your mind right now, is being carried along in that current at 1,400,000 miles per hour. You are not watching the river from the bank. You are in it, have always been in it, will always be in it for as long as you and everything descended from you exists. The speed is real. The direction is real. The destination, uncertain and impossibly distant, is real. And none of it changes the weight of your breathing, or the warmth of wherever you're lying tonight, or the particular quality of the silence in the room around you. The cosmic and the intimate coexist without contradiction, each one making the other stranger and more precious than it would be alone. Speed at this scale is ultimately a meditation on patience. The universe does not rush. It does not need to. With timescales measured in trillions of years, even a speed of 1,400,000 miles per hour is a gentle, unhurried drift. The Great Attractor is not pulling urgently. It is simply there, as it has always been, exerting its quiet and irresistible influence across the void. And we are moving toward it the way the night moves toward dawn, steadily and without drama, in a direction that was set long before any of us arrived, and will continue long after every light we have ever known has finally gone out. There is more to the universe than you can see. This is not a metaphor or a philosophical observation. It is a precise, quantitative, scientifically verified statement about the actual composition of everything that exists. The stars, the galaxies, the gas clouds, the planets, the dust, every single thing that emits or reflects light, every object that has ever been observed through any telescope in human history, all of that luminous matter added together accounts for only about 5% of the total mass and energy content of the universe. 5%. The remaining 95% is something else entirely, something that does not interact with light in any way we can currently detect, something that reveals its existence only through its gravitational effects. on the matter we can see. And when you're trying to understand what is pulling our galaxy toward the Great Attractor, that invisible 95% is not a minor footnote. It is the engine. The story of dark matter's discovery is in some ways parallel to the story of the Great Attractor itself. It begins not with a dramatic revelation, but with a persistent, troubling discrepancy between what the equations predicted and what the observations showed. In the 1930s, the Swiss astronomer Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies about 320 million light-years from Earth. He calculated the mass of the cluster by measuring how fast the individual galaxies within it were moving, using the logic that a more massive cluster would produce faster orbital velocities in its member galaxies, just as a more massive star produces faster orbital speeds in its planets. What he found was that the galaxies were moving far too fast. The visible mass of the cluster, all the stars and gas he could observe, was nowhere near enough to gravitationally contain galaxies moving at those speeds. They should have flown apart long ago. Something invisible, something massive, had to be holding them together. Zwicky called it Dunkel Materie, dark matter. For decades, the idea remained controversial, an interesting anomaly that many physicists hoped would be explained away by better data or more careful calculations. Then in the 1970s, the American astronomer Vera Rubin, working with her colleague Kent Ford, conducted careful measurements of how stars within individual galaxies orbit their galactic centers. The expectation, based on visible mass alone, was that stars in the outer regions of a galaxy should orbit more slowly than stars near the center, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. What Rubin found instead was that the orbital velocities of stars in the outer regions of galaxies were not declining at all. They stayed flat or even slightly increased out to the very edges of the visible disk. The only way to explain this was if there was a vast halo of invisible mass surrounding each galaxy, extending far beyond the visible stars, providing the extra gravitational pull that kept outer stars orbiting at unexpectedly high speeds. The evidence for dark matter was no longer a single anomaly. It was everywhere. We now understand, or rather we now have strong evidence to conclude, that dark matter outweighs ordinary visible matter by a ratio of roughly 5-1. For every gram of normal matter in the universe, there are approximately 5 grams of dark matter. The Milky Way itself is surrounded by an enormous dark matter halo, extending hundreds of thousands of light-years beyond the visible disk of stars, a vast invisible sphere of gravitational influence that is actually responsible for much of the galaxy's structural integrity. Without its dark matter halo, the Milky Way's stars would not be able to orbit at the speeds they do, and the galaxy as we know it could not exist in its current form. Dark matter is not a peripheral feature of our galaxy. It is the skeleton around which the visible galaxy is draped. Now bring this back to the Great Attractor. The gravitational pull we feel from that direction, the force driving the peculiar velocity of the Milky Way and hundreds of thousands of its neighbouring galaxies, is not produced by the visible matter in the Norma cluster and the Shapley supercluster alone. The vast majority of the mass producing that pull is dark matter. The galaxy clusters in the attractor region are themselves embedded in dark matter halos far larger and more massive than the visible clusters themselves. The filaments and walls of the cosmic web that connect those clusters are threaded with dark matter. The voids between the filaments are not truly empty, but suffused with a lower density distribution of dark matter that still contributes gravitational influence across enormous distances. When you add it all up, the visible matter in the Great Attractor region is perhaps 20% of the total mass responsible for the gravitational flow we are caught in. The other 80% is dark, invisible, detectable only through its effects. Here is the thing most people do not realize about dark matter's role in cosmic structure. dark matter did not just add mass to structures that would have formed anyway. It is the reason large structures formed at all. In the very early universe, shortly after the Big Bang, the distribution of matter was almost but not quite perfectly uniform. There were tiny density fluctuations, regions where the matter was very slightly denser than average, and regions where it was very slightly less dense. Ordinary matter alone, buffeted by radiation pressure and thermal motion, would have smoothed out these fluctuations before they could grow into anything significant. But dark matter, which does not interact with light and therefore was not affected by radiation pressure, could begin clumping under its own gravity immediately. It formed the first gravitational wells, the scaffolding into which ordinary matter later fell, condensing and cooling and eventually forming the first stars and galaxies. Without dark matter, the universe might today be a nearly uniform fog of hydrogen gas, rather than the rich structured landscape of galaxies, clusters, and superclusters we actually observe. The great attractor in this sense is a dark matter structure first and a galaxy cluster second. The visible galaxies we can observe in that region, the Norma cluster and its companions, are the luminous traces of a far larger dark matter concentration that preceded them. The dark matter gathered first, its gravity pulling in ordinary matter over billions of years, which condensed into stars and galaxies that now mark the location of the dark matter concentration, the way buoys mark the location of a reef beneath the water's surface. We see the buoys, we infer the reef, and the reef is what is actually pulling us. What dark matter actually is remains one of the most important, unsolved problems in all of physics. We know what it is not. It is not ordinary atoms in any form, not dark gas clouds, not dim stars, not black holes of the conventional type, not any particle that has yet been directly detected in any laboratory on Earth. The leading candidates are various types of hypothetical particles, weakly interacting massive particles known as WIMPs, axions, sterile neutrinos and others, each with different predicted properties, and each the subject of ongoing experimental searches. Enormous underground detectors filled with liquid xenon or germanium crystals have been built specifically to catch a dark matter particle in the act of colliding with ordinary matter. So far, none have succeeded. The dark matter remains dark, not just to our telescopes, but to our most sensitive particle detectors as well. And yet it is there. It has to be there. The gravitational evidence is overwhelming, consistent, and confirmed by multiple independent lines of observation spanning from the rotation curves of individual galaxies to the large-scale structure of the cosmic web, to the precise pattern of temperature fluctuations in the cosmic microwave background. Radiation left over from the Big Bang. Dark matter is the invisible engine driving the formation and evolution of everything we can see, including the great attractor, including the flow of Laniakea, including the motion of the Milky Way tonight. 5% of the universe is visible. The rest is mystery. And the mystery, as it turns out, is doing most of the work. If you could somehow step outside the observable universe and look back at it from a distance, great enough to see the whole thing at once, the first thing that would strike you is not the brightness of the galaxies or the darkness of the voids. It would be the structure, the shape, the way everything is arranged not randomly, not uniformly, but in a vast and intricate pattern that looks with an uncanniness that has unsettled many cosmologists, remarkably like something biological, like a neural network, like the web of neurons in a human brain, or the mycelium of a forest fungus spreading through dark soil. Long, thin filaments of matter stretching across hundreds of millions of light years, connecting at dense nodes where galaxy clusters congregate, surrounding enormous empty voids where almost nothing exists. This is the cosmic web, and it is the largest structure in the universe, the scaffolding on which everything else is built. The cosmic web is not a metaphor or a visual convenience invented to help us describe the universe's arrangement. It is a real, physical structure, a consequence of the same gravitational physics and dark matter dynamics we discussed in the last chapter, playing out over 13.8 billion years of cosmic evolution. In the beginning, the universe was nearly uniform, a hot, dense plasma, with only the faintest ripples of density variation seeded by quantum fluctuations in the first fractions of a second after the Big Bang. Dark matter began clumping along those density ridges almost immediately, forming the first thin sheets and filaments of overdense material. Ordinary matter followed, pulled into those dark matter structures by gravity, cooling and condensing into gas clouds and eventually into stars and galaxies. Over billions of years, gravity continued its patient work, draining matter from the voids into the filaments and draining matter from the filaments into the nodes at their intersections, building the web ever more sharply into the structure we observe today. The filaments of the cosmic web are extraordinary objects in their own right. They are not solid structures, not rods or threads of matter in any conventional sense. They are elongated concentrations of dark matter and ordinary matter, tens of millions of light years long and millions of light years wide, within which galaxies are strung like beads on a wire. The density within a filament is much higher than the average density of the universe, but still extraordinarily low by any earthly standard. Space is always mostly empty, even within the densest filaments. What matters is the relative concentration, enough to gravitationally shepherd matter along the filament's length toward the massive nodes at each end. Those nodes are where galaxy clusters form, where the filaments converge from multiple directions and pour their contents into a common gravitational basin. The Great Attractor region is one such node, a place where multiple filaments of the cosmic web meet and deposit their matter into a structure of extraordinary mass. Between the filaments lie the voids. These are regions of space that are genuinely, almost completely empty, vast bubbles of near nothingness that can span hundreds of millions of light years across. The voids are not perfectly empty. They contain a sparse scattering of galaxies, isolated wanderers, that happen to occupy the low-density regions between the filaments. But compared to the filaments and nodes, they are as close to nothing as the universe gets on large scales. The voids are, in a sense, the universe's negative space, defined not by what they contain, but by what surrounds them. And they are enormous. Some of the largest known voids span more than 1 billion light years across, making even the Laniakea supercluster look compact by comparison. Most of the volume of the universe is void. Most of the matter of the universe is packed into the thin filaments and dense nodes that form the web surrounding those voids. The cosmic web was predicted, theoretically, before it was observed directly. In the 1980s, computer simulations of cosmic structure formation, run on the early supercomputers of that era, began producing virtual universes that showed exactly this kind of filamentary structure. The simulations started with the known, initial conditions of the early universe, applied the known laws of gravity and dark matter dynamics, and let them run forward in time. What emerged again and again across many different simulations and many different research groups was a web. Filaments, nodes, voids. The pattern was robust, appearing in every simulation, regardless of the specific parameters used, as long as dark matter was included. When the actual large-scale surveys of the real universe began to return data in the 1990s and 2000s, the match between the simulations and the observations was striking. The universe looks the way the physics said it should. The web is real. Here is the thing most people do not realize about the cosmic web and its relationship to the Great Attractor. The Great Attractor is not an isolated object that happens to be pulling nearby galaxies toward it. It is a node in the web, a convergence point where filaments from multiple directions deliver matter and energy into a common basin. The flow of galaxies we have been tracing throughout tonight, the peculiar velocities that the Seven Samurai measured in the 1980s, the river of Laniakea, all of it is the large-scale expression of matter flowing along the filaments of the cosmic web toward their nearest massive node. The Great Attractor is the drain at the bottom of our local section of the web, and the filaments are the channels that guide the flow. Understanding the web is understanding why the attractor exists and why everything in our neighborhood is moving toward it. The James Webb Space Telescope, launched in December of 2021 and delivering its first science results in 2022, has begun to provide extraordinary new views of the cosmic web in its earliest stages. By looking at objects so distant that their light has been travelling toward us for more than 13 billion years, Webb can observe the universe as it was only a few 100 million years after the Big Bang, when the first filaments were just beginning to form and the first massive galaxy clusters were assembling at the nodes. What Webb has found has surprised even experienced cosmologists. Structure formed earlier and more dramatically than many models predicted. Massive galaxies and dense clusters appear in the early universe in numbers and at scales that challenge existing theories of how quickly the web can assemble. The cosmic web, it seems, built itself faster than we thought possible. There is something deeply calming, paradoxically, about the scale of the cosmic web. When you hold in your mind the image of this structure, filaments hundreds of millions of light years long, nodes where galaxy clusters congregate at their intersections, voids a billion light years across lying in the spaces between, the ordinary anxieties of human life become very quiet, not irrelevant, never irrelevant, but quiet in the way that things become quiet when you place them against a backdrop large enough to absorb them without effort. You are a small warm creature on a small rocky planet, orbiting one star among 400 billion in one galaxy, among 100,000 in one supercluster, among thousands, in a web that spans the entire observable universe. And the web has been here, in some form, since nearly the beginning of everything, and it will be here, in some evolved future form, long after every star currently burning has exhausted its fuel. The web endures, and somewhere within it, patient and invisible, the Great Attractor waits, at the end of a river that has been flowing toward it since before the Earth was born. Here is the question that sits at the heart of everything we have been exploring tonight. The one that, once you ask it clearly, produces a particular kind of quiet vertigo. Our galaxy is moving toward the Great Attractor. It has been moving toward it for billions of years. It is moving toward it right now, at this very moment, at 1,400,000 miles per hour. So the natural question, the one that follows as inevitably as night follows sunset, is this: will we ever get there? Will the Milky Way, carried along in the river of Laniakea, eventually reach the gravitational basin toward which everything has been flowing for so long? And the answer, when you work through the physics carefully, is one of the most quietly devastating conclusions in all of modern cosmology. Almost certainly not. And the reason why tells us something profound and unsettling about the ultimate fate of the universe itself. To understand why arrival may be impossible, you need to understand something we have not yet discussed in detail tonight. Something called dark energy. We have spent time with dark matter, the invisible mass that makes up most of the gravitational substance of the universe. Dark energy is different, entirely different. Where dark matter is a form of invisible mass that behaves like matter in most respects, exerting gravitational attraction and clumping into structures. Dark energy is something stranger and more difficult to conceptualize. It is a property of space itself, a form of energy inherent to the vacuum, to empty space, that produces not gravitational attraction, but gravitational repulsion. Not a pull, but a push. And it is pushing the universe apart, accelerating the expansion of space at a rate that, on the larger scales, is overcoming the gravitational pull of everything in it. Dark energy was discovered, or rather inferred, in 1998, when two independent teams of astronomers studying distant supernova made an observation that shocked the scientific community. They were using a specific type of stellar explosion, called a Type Ia supernova, as a standard candle, a light source of known intrinsic brightness that could be used to measure cosmic distances precisely. The expectation was that the expansion of the universe, set in motion by the Big Bang, would be gradually slowing down over time as gravity pulled matter back together. What they found instead was the opposite. The expansion was accelerating. Distant galaxies were receding faster than nearby ones, not just because they were farther away in an expanding universe, but because the rate of expansion itself was increasing. Something was driving the universe apart with increasing force. That something is what we call dark energy, and it constitutes approximately 68% of the total energy content of the universe. Dark matter is about 27%. Ordinary visible matter, everything we can see and touch and measure, is the remaining 5%. Now place dark energy into the picture of the Great Attractor. The attractor is pulling our galaxy toward it at 1,400,000 miles per hour. But the expansion of the universe, driven by dark energy, is simultaneously carrying the attractor away from us. At the distance of the Great Attractor region, roughly 250 million light-years, the recession velocity due to cosmic expansion is already significant. The two velocities, the infall velocity toward the attractor and the recession velocity due to expansion, are in competition, and here is the critical point. Dark energy causes the expansion to accelerate over time. As time passes, the recession velocity of distant objects increases, not decreases. The universe is not slowing down, it is speeding up, which means that the competition between gravity and expansion is one that gravity, on the largest scales, is gradually losing. Here is the thing most people do not realize about what this means for our journey toward the Great Attractor. On the scale of Laniakea, our local supercluster, gravity is still winning for now. The 500 million light-years of Laniakea represent a region where the gravitational forces are strong enough to maintain the coherence of the structure and drive the infall flows we observe. The river is still flowing toward the attractor, but at larger scales, beyond Laniakea, the expansion is already dominant. Galaxy clusters outside our local supercluster are being carried away from us faster than any gravitational force can overcome. The observable universe is, in a sense, shrinking, not in size but in the number of objects that we will ever be able to interact with gravitationally. Objects beyond a certain distance are already receding faster than the speed of light, carried away by the expansion of space itself, and we will never reach them, no matter how long we travel. The Great Attractor sits in an interesting position in this competition. It is close enough that we are still clearly falling toward it. The gravitational flow is unambiguous and measurable, but it is far enough that the expansion is a meaningful competitor. Over billions of years, as dark energy continues to accelerate the expansion, the balance will shift. The infall velocities will decrease relative to the recession velocities. The river will slow. The flow will weaken, and at some point in the deep future, the expansion may entirely overcome the gravitational pull of the attractor, and the flow will stop and then reverse as the accelerating expansion carries even Laniakea's member galaxies apart from each other. The river does not reach the sea. It evaporates before it arrives. There is something almost mythological about this conclusion. We are falling toward a destination we will never reach, drawn by a force we cannot feel, moving at a speed we cannot perceive, in a race against an expanding universe that will eventually win. It has the quality of certain ancient stories, the unreachable goal, the eternal approach, the destination that perpetually recedes, except that in this case, It is not a metaphor, it is physics. It is what the equations say, and the equations have been right about everything else they have predicted about the large-scale structure and fate of the cosmos. We are in the river is real, and the sea we are flowing toward will, in all likelihood, recede beyond our reach before we ever arrive. But here is what matters, and why this conclusion, properly understood, is not cause for despair, but for a strange and quiet wonder. The journey itself is the structure. The flow of Laniakea toward the great attractor is not merely a transit between a starting point and a destination. It is the mechanism by which cosmic structure organizes itself, by which matter congregates and complexity increases, and on at least one small rocky world, in one of those flowing galaxies, consciousness emerges and begins to ask questions about where it is going and why. The river produced us. The river is carrying us. Whether or not it ever reaches the sea is, in the deepest sense, secondary to the extraordinary fact that it is flowing at all, and that something within it is aware enough to notice. We are the universe watching itself fall through the dark, and that tonight is enough. We have been speaking tonight as though the great attractor is the only significant gravitational force shaping the motion of our galaxy. And in the context of our immediate cosmic neighborhood, within the basin of Laniakea, it is the dominant influence, the primary drain toward which the river flows. But the universe does not operate through single forces in isolation. It operates through the overlapping, competing, reinforcing influence of many structures simultaneously, each one tugging and pulling and nudging the matter in its vicinity, each one part of a larger gravitational landscape that is, when you step back far enough to see the whole picture, breathtakingly complex. The great attractor is real. Its pull is real, but it is not alone. And understanding what else is out there, pushing and pulling from different directions, gives us a much richer and more accurate picture of why our galaxy moves the way it does. Let us begin with something that took decades longer than the great attractor to identify and name, partly because the concept required a different way of thinking about cosmic motion. If a gravitational attractor pulls matter toward it by being denser than its surroundings, then the logical complement of an attractor is a repeller, a region of space that is significantly less dense than average, and therefore pushes matter away from it not through any exotic force, but simply through the asymmetry of gravitational pull. In a perfectly uniform universe, every region would pull equally in all directions, and nothing would move preferentially anywhere. In the lumpy, structured universe we actually inhabit, regions of higher than average density pull matter toward them, while regions of lower than average density effectively push matter away, because the pull from the denser, surrounding regions overwhelms the weak pull from the void itself. Astronomers call these low-density regions that drive matter outward dipole repellers. In 2017, a team led by Yehuda Hoffman of the Hebrew University of Jerusalem published a landmark paper identifying a specific large-scale structure they called the dipole repeller, a vast cosmic void located in the direction roughly opposite the great attractor from our position in the general direction of the constellation Gemini. The dipole repeller is a region of significantly below average density, a place where matter is sparse and the gravitational landscape slopes sharply away in all directions. Matter in the vicinity of the dipole repeller flows away from it, pushed outward by the differential gravitational pull of the denser surroundings, and crucially, the direction of that outward flow is toward the great attractor. The dipole repeller and the great attractor work together, one pushing and one pulling, both contributing to the same net motion of our galaxy across the cosmos. Our peculiar velocity is not caused by the attractor alone. It is the combined result of being pulled from one direction and pushed from another, and the two effects add together to produce the total motion we measure. The discovery of the dipole repeller was significant because it resolved a long-standing tension in the data. When astronomers tried to account for the full peculiar velocity of the Milky Way using only the gravitational pull of the Great Attractor and the Shapley supercluster, the numbers never quite added up completely. There was always a component of the motion that seemed to come from the opposite direction, as though something was pushing from behind as well as pulling from the front. The dipole repeller provided that missing piece. It is the push that complements the pull, the void that collaborates with the overdensity, together producing the full complexity of our galaxy's motion through space. The cosmic landscape is shaped by both its mountains and its valleys, and you cannot understand why water flows the way it does unless you know where both the high ground and the low ground are. Beyond the dipole repeller, the gravitational landscape extends in all directions, with structures of varying mass and distance contributing their own components to the overall flow. The Perseus-Pisces supercluster, a massive concentration of galaxy clusters located roughly 250 million light-years away in the direction of the constellations Perseus and Pisces, exerts a gravitational influence on our region of space from a direction roughly perpendicular to the Great Attractor pull. It is not a dominant force on our galaxy's motion, but it is measurable, a sideways nudge in the broader context of our cosmic trajectory. The Coma supercluster, the Hercules supercluster, the various other concentrations of mass scattered across the local cosmic web, each contribute their own gravitational voice to the chorus, each pulling from a different direction with a different intensity, each shaping the net motion of everything in their vicinity. Here is the thing most people do not realize about the overall gravitational environment our galaxy inhabits. The motion of the Milky Way that we have been discussing throughout tonight is not a simple straight-line fall toward a single target. It is a complex multi-component drift through a gravitational landscape shaped by dozens of overlapping influences. The Great Attractor provides the dominant pull. The Shapley supercluster behind it adds additional depth. The dipole repeller pushes from the opposite direction. Smaller structures contribute minor corrections from various angles. The net result of all these influences is the peculiar velocity we measure, but that velocity is not fixed. It changes slowly over cosmic time as the relative positions of all these structures shift, as some concentrations grow denser by accreting more matter, and others begin to be eroded by the accelerating expansion of the universe. The gravitational landscape is not a static map. It is a slowly evolving terrain, and our trajectory through it shifts accordingly. What makes this multi-attractor picture genuinely fascinating from a cosmological perspective is what it reveals about the nature of the cosmic web itself. The web is not a uniform structure with a single dominant node. It is a network with many nodes of varying mass connected by filaments of varying density, each node embedded in its own web of gravitational influence, each filament both drawing matter from the voids and funneling it toward the nodes at its ends. Our galaxy sits within this network, pulled and pushed by multiple nodes simultaneously. Its trajectory, the vector sum of all those competing influences. We are not passengers on a train with a single destination. We are leaves in a river system that has many tributaries, many currents, and many confluences, moving always toward lower gravitational potential, always following the slope of the landscape, always in motion, and always embedded in a context larger than any single structure we can name. The Shapley supercluster deserves one more mention here, because recent surveys have suggested that its gravitational influence may extend even further than previously appreciated, and that it may itself be part of an even larger structure, sometimes called the Shapley concentration, a complex of superclusters and filaments that together represent one of the most massive gravitational anomalies in the observable universe within 1 billion light-years. If this is correct, then the flow of matter toward the Great Attractor region is not just a local, Laniakea phenomenon, but part of a much larger gravitational current that extends across scales we are only beginning to map. Each new survey, each new instrument, each new generation of cosmologists peering at the large-scale structure of the universe seems to find that the relevant scales are larger than the previous generation thought. The universe keeps revealing that the frame we are using is always slightly too small. And so we sit tonight at the intersection of all these forces, pulled from one direction and pushed from another, embedded in a web of gravitational influences that spans hundreds of millions of light years in every direction, moving through the dark at a speed our bodies cannot feel toward a destination our lifetimes cannot reach. The Great Attractor is the most prominent voice in this gravitational chorus, but it is a chorus, not a solo, and the music it makes, if you could somehow hear it, would be the sound of the entire observable universe organizing itself through gravity across billions of years, endlessly, patiently, in the dark. At some point in a conversation about things this large, the mind naturally wants to come home. It has been out in the deep cosmic dark, measuring superclusters and tracing velocity flows across 500 million light years. And eventually, it turns around and asks the most human question of all. What does any of this mean for me, for the planet I live on, the air I breathe, the people I love, the brief and particular life I am living right now in this specific moment? It is not a small question, even if it can feel like a retreat from the grandeur of what we have been discussing. It is actually the most important question, because the whole point of looking outward at the scale of the cosmos is not to feel small and helpless. It is to understand where you are, and understanding where you are changes everything about how you see yourself. So let us be precise about what the Great Attractor means for Earth. In practical terms, in the timescale of a human life, or 1,000 human lives, or 1,000,000 years of human civilization, it means nothing at all that you would notice. The motion of our galaxy toward the Great Attractor is real and ongoing, but it produces no effect that registers at the scale of planets or people. Earth's orbit around the Sun is not perturbed by it. The Sun's orbit around the galactic center is not meaningfully affected by it. The structure of the solar system, the tilt of Earth's axis, the length of the day, the rhythm of the seasons, the behavior of the oceans and the atmosphere, none of these are influenced in any detectable way by the gravitational pull of a mass concentration 250 million light years away. The pull is real, but its effects at our scale are so diluted by distance as to be, for all practical purposes, non-existent. But here is what I find genuinely moving about that fact. It means that everything that has ever happened on Earth, every single event in the 4.5 billion year history of this planet, every extinction and explosion of life, every ice age and warm period, every mountain range that rose and eroded and rose again, every ocean that formed and dried and reformed, every organism that ever lived and died on this world, all of it has unfolded while Earth was aboard a galaxy that was silently, invisibly, continuously falling toward the Great Attractor. The dinosaurs walked the Earth while we were falling. The first oceans formed while we were falling. The first cells assembled themselves in shallow tidal pools while we were falling. Every chapter of Earth's history has been written aboard a vessel in motion, and not one living thing that ever existed here had any awareness of the journey. There is something quietly extraordinary about picturing the history of life on Earth in this context. When the first photosynthetic bacteria began releasing oxygen into the early atmosphere, roughly 2.4 billion years ago, our galaxy had already been falling toward the Great Attractor for billions of years before that. When the first fish crawled onto land, roughly 375 million years ago, we were already deep in the current of Laniakea. When the first human beings looked up at the night sky and began to wonder what the stars were, our entire galaxy had been in motion toward an invisible gravitational basin for longer than the Earth had existed. Wonder has always been the appropriate response to the night sky. It turns out we just did not know how much there was to wonder about. Now consider the future in the same terms. Earth has roughly another 4 to 5 billion years before the Sun exhausts its hydrogen fuel and begins to swell into a red giant, eventually engulfing the inner planets, including, in all likelihood, our own. Over those billions of years, the Milky Way will undergo its own dramatic transformation. Approximately 4 billion years from now, the Andromeda Galaxy will begin its final approach, and the two galaxies will begin a slow merger, a process that will unfold over hundreds of millions of years, producing a new combined galaxy that astronomers have already nicknamed Milkomeda. During this entire process, during the collision and merger of two of the largest galaxies in the local group, our solar system will almost certainly survive, perturbed but not destroyed, because the distances between individual stars are so vast that direct stellar collisions are extraordinarily rare even during galactic mergers. The night sky will change dramatically, lit by new star-forming regions ignited by the collision, but Earth, if it still exists, will continue orbiting its star through it all. And through all of that, the motion toward the Great Attractor will continue. The merged Milkomeda galaxy, carrying with it whatever remains of Earth and the solar system, will still be part of the flow of Laniakea, still drifting in the same direction, still caught in the same gravitational current that has been drawing matter toward the attractor basin for billions of years. The destination does not change because the vessel changes shape. The river does not stop flowing because two of its currents merge. On the largest scales, the story continues regardless of the dramas playing out within it. And the story is always the same. Gravity pulls, matter flows, structure grows, and the universe evolves in the direction its initial conditions and its fundamental laws have been pointing it since the very first moment of its existence. Here is the thing most people do not realize when they first absorb the idea that our galaxy is being pulled through space by an invisible gravitational giant. It does not threaten us. It is not a danger. It is not something we need to worry about in any concrete sense, now or ever, at the scale of human civilization. The terrifying quality of the Great Attractor is not that it endangers Earth. It is that it exists at all, that the universe contains structures of this scale, operating on timescales, this vast, that the familiar world of human experience is embedded within a cosmic drama so enormous that our entire species' history occupies less than a single frame of the film. That is the vertigo the Great Attractor produces. Not fear of destruction, but astonishment at scale. Not danger, but depth. And that astonishment, properly felt, is one of the most valuable experiences available to a human mind. It reorders priorities. It quiets anxieties that, in the light of the cosmos, reveal themselves as relatively small. It produces a particular kind of humility that is not self-diminishing, but genuinely liberating. The recognition that you are part of something so much larger than yourself, that the boundaries of the self become temporarily permeable, and you feel, briefly and beautifully, the connection between your own brief existence and the vast, ancient, ongoing story of the universe itself. Earth is a tiny world. Our lives are brief, but we are here, aware, looking outward, understanding something about where we are and where we are going. That is not nothing. In 13.8 billion years of cosmic history, it may be one of the rarest things of all. There is no sound in space. This is one of the first things most people learn about the cosmos, and it is true in a very precise physical sense. Sound requires a medium, molecules that can be compressed and rarefied in waves, transmitting mechanical energy from one point to another. The near-perfect vacuum of interstellar and intergalactic space contains so few particles per cubic meter that sound waves as we understand them cannot propagate. If a star explodes somewhere in the galaxy, the blast wave travels outward through the surrounding gas and plasma, but that wave would dissipate long before it crossed the vast emptiness between galaxies. And at the scale of the Great Attractor, the scale at which entire superclusters of galaxies are being drawn through space across hundreds of millions of light years, there is no medium capable of carrying any signal of that motion whatsoever. The pull operates in complete, absolute, unbroken silence, and that silence, when you sit with it long enough, becomes one of the most unsettling things about the whole story. Think about what silence means at this scale. The Milky Way, 300 billion stars, and everything orbiting them is moving at 1,400,000 miles per hour toward a gravitational concentration 250 million light years away. That motion has been continuous for billions of years. It will continue for billions more, and there is no signal, no alarm, no vibration, no whisper of any kind that announces it or accompanies it or could ever be detected by any instrument sensitive to sound. The most powerful motion in our cosmic neighborhood, the gravitational choreography of 100,000 galaxies being drawn together across 500 million light-years, happens in a silence so complete that the word silence itself seems inadequate. Silence implies the absence of something that could be there. This is something more fundamental. This is a kind of quiet that is built into the nature of space itself. Now bring this silence into contact with the Fermi paradox, that famous and deeply uncomfortable observation made by the physicist Enrico Fermi in 1950, when he asked a question at lunch that has haunted science ever since. The universe is approximately 13.8 billion years old. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars, and around those stars, as we now know, planets are common. The conditions for life, as we understand it, liquid water, organic chemistry, stable energy sources, seem to exist across vast numbers of worlds. By probabilistic reasoning, civilizations should be common. Some should be far older than ours, with millions or billions of years of technological development. And yet, no radio signals, no signs of engineering at cosmic scales, no evidence of visitation, no response to any signal we have sent. The universe, examined with our best instruments, appears completely, bewilderingly empty of other minds. Fermi's question was simple and devastating. Where is everybody? The silence of the Great Attractor connects to the Fermi paradox in a way that I find particularly thought-provoking. Every civilization that has ever existed anywhere in the observable universe, if any have existed at all, has been subject to the same gravitational flows we have been discussing tonight. Every civilization in Laniakea has been falling toward the Great Attractor at roughly the same speed we are, carried along in the same river, embedded in the same cosmic web. If there are civilizations in the Norma cluster itself, they are even closer to the attractor, falling faster, perhaps already seeing the structure of the surrounding supercluster differently than we do from our more distant vantage point, and none of them, in all of cosmic history, have sent us a single detectable signal. The silence is not just local, it is cosmic, and it encompasses not just empty space, but the gravitational drama playing out across hundreds of millions of light years. Here is the thing most people do not realize about the silence and what it might mean. One of the proposed explanations for the Fermi paradox is that the development of technology capable of interstellar communication or travel is so difficult, or so dangerous, or so improbable that civilizations simply do not survive long enough to broadcast their presence across cosmic distances. On the timescales of the Great Attractor, where billions of years are the relevant unit of measurement, the entire history of human civilization, from the first stone tools to the present day, is an interval so brief as to be nearly invisible. If civilizations routinely destroy themselves within a few thousand years of developing radio technology, then even a galaxy containing millions of civilizations might, at any given moment, host only a handful simultaneously, scattered across such vast distances that their signals have not yet had time to reach each other. The silence may not mean emptiness, it may mean brevity, and that possibility is, in its own way, the most terrifying interpretation of all. The pull of the Great Attractor operates on timescales that dwarf the history of intelligence on Earth many times over. Gravity does not notice us. It does not adjust its schedule to accommodate the brief window during which conscious beings exist on any given world and look outward and wonder. The gravitational flow of Laniakea has been operating for billions of years before any mind anywhere in the supercluster looked up and noticed it, and it will continue operating for billions of years after every mind in Laniakea has gone quiet. The silence of the pull is not indifference in any emotional sense. The universe does not have emotions, but it has timescales, and those timescales make the entire history of awareness in the cosmos seem like a candle lit briefly in a very dark room, burning for a moment and then going out, while the room itself, vast and patient, continues exactly as before. And yet the candle matters. This is the tension at the heart of the cosmic perspective, the thing that makes it uncomfortable in a productive way. The universe is silent and vast and ancient and utterly indifferent to the existence of minds within it. And minds exist within it anyway, briefly, improbably, and with a capacity for wonder that seems almost disproportionate to their physical significance. You are an arrangement of atoms on a small planet in a middling galaxy in a supercluster of 100,000 galaxies, all of it falling through the dark toward an invisible attractor at a speed you cannot feel. And you're thinking about it. You are here tonight, letting the scale of it arrive, sitting with the silence of it, finding in that silence not emptiness but a kind of resonance. The pull is silent, but the awareness of the pull is not. And that awareness, however brief, is the most remarkable thing in this part of the universe that we know of. When you lie quietly in the dark after tonight and think about the silence of the Great Attractor, I hope you feel both things simultaneously. The genuine smallness of a single human life measured against the scale of what we have been exploring, and the genuine astonishment of the fact that something that small can contain a mind large enough to comprehend, at least partially, the thing that is carrying it. The pull is silent, the question it inspires is not, and as long as something's asking the question, the silence has not entirely won. There is a particular kind of intellectual honesty that the best science eventually demands, and it is not the honesty of confident proclamation, but the honesty of careful admission. We have spent tonight exploring the Great Attractor with a level of detail and precision that might give the impression that this is a solved problem, a mystery that has been investigated and catalogued and filed away in the completed section of the Cosmic Encyclopedia. It is not. The Great Attractor remains, in important and fundamental ways, an open question. The outline of the answer is visible. The broad strokes are confirmed by multiple independent lines of evidence, but the details, the precise mass, the exact structure, the full extent of the gravitational influence, the ultimate relationship between the attractor and the larger cosmic web beyond it, all of these remain areas of active research, genuine uncertainty, and in some cases real scientific disagreement. And I think that is worth sitting with tonight, because the uncertainty is not a failure. It is where the story is still alive. The most immediate and persistent obstacle to understanding the Great Attractor remains the zone of avoidance. Despite decades of radio and infrared surveys that have dramatically improved our view of the regions behind the galactic plane, the zone of avoidance still hides a significant fraction of the sky from detailed observation. The surveys have confirmed galaxy clusters in the attractor region and resolved the broad outline of what is there, but the fine structure, the precise distribution of mass within the attractor region, the exact locations and masses of individual clusters, and the filaments connecting them remains poorly constrained compared to our knowledge of regions of sky where optical telescopes can operate freely. We are still in a meaningful sense reading the Great Attractor through frosted glass, able to make out the shapes but unable to resolve the fine detail that a clean view would provide. The mass of the Great Attractor is another area of genuine uncertainty. Estimates based on the peculiar velocity flows, the approach of measuring how fast nearby galaxies are moving, and inferring what mass is required to produce those velocities, have varied considerably over the decades as the quality and coverage of the velocity surveys improved. Early estimates suggested a mass equivalent to tens of thousands of galaxies. More recent surveys, incorporating the broader context of Laniakea and the contribution of the Shapley supercluster, have refined those estimates, but have also complicated the picture by making it clear that the relevant mass is distributed across a much larger region than initially assumed. The Great Attractor is not a compact object with a clean boundary and a precise mass. It is a broad gravitational basin whose extent and total mass depend on how you define the edges of the system, which is itself a matter of ongoing scientific discussion. The relationship between dark matter and the visible structure in the attractor region is also incompletely understood. We know that dark matter dominates the mass budget of every large structure in the universe, and the Great Attractor region is no exception. But the precise distribution of dark matter within and around the attractor, the shape and extent of the dark matter, halos surrounding the Norma cluster and the other galaxy clusters in the region, and the way dark matter filaments connect those clusters to the larger cosmic web, are all quantities that are inferred indirectly rather than measured directly. Dark matter cannot be seen. It can only be weighed by its gravitational effects on visible matter, and the weighing is only as precise as the visible matter surveys that underpin it. As those surveys improve, our picture of the dark matter distribution in the attractor region will improve too. But right now, the invisible engine driving the pull remains, fittingly, only partially visible to our instruments. Here is the thing most people do not realize about the current state of knowledge regarding the Great Attractor and the larger flow structures of which it is part. The boundary of Laniakea, the supercluster whose gravitational basin is defined by the attractor, is itself a subject of ongoing scientific debate. The 2014 paper by Tully and colleagues that defined Laniakea used a specific methodology, tracing the velocity flows to find the watershed boundaries of the gravitational basin. Other researchers, using different methodologies and different definitions of what constitutes a coherent gravitational structure, have arrived at somewhat different pictures of how Laniakea should be defined. Whether it truly constitutes a gravitationally bound structure in the long-term sense, and whether the Great Attractor is best understood as the center of Laniakea or as one node in a larger network that includes the Shapley concentration and other massive structures beyond. The map is still being drawn, and different cartographers are making different choices about where to put the boundaries. Beyond Laniakea, the picture becomes even less certain. There are hints in the velocity data of flows that extend beyond the 500 million light-years of our local supercluster, currents of motion that suggest the gravitational influence of even more distant and massive structures reaching into our neighborhood from further away. The Shapley supercluster is the best characterized of these, but there may be additional contributions from structures that are even further away and less well mapped. The observable universe extends approximately 46 billion light-years in every direction from Earth, and we have detailed velocity surveys of only a small fraction of that volume. The regions beyond our current survey boundaries may contain structures with gravitational influences that we have not yet detected or accounted for. The Great Attractor may itself be falling towards something even larger that lies beyond our current horizon of knowledge. The next generation of astronomical instruments offers genuine hope for resolving some of these uncertainties. The Square Kilometre Array, a radio telescope being built across sites in South Africa and Australia with a total collecting area of 1 square kilometre, will conduct the most sensitive and comprehensive radio surveys ever attempted when it reaches full operation later this decade. It will peer into the zone of avoidance with unprecedented resolution, mapping the galaxy distribution behind the galactic plane in detail that current instruments cannot achieve. The Euclid Space Telescope, launched in 2023 by the European Space Agency, is conducting a survey of galaxy shapes and positions across a vast region of the sky, building a three-dimensional map of the large-scale structure of the universe that will dramatically improve our understanding of the cosmic web and the velocity flows within it. And the Vera Rubin Observatory in Chile, beginning its legacy survey of space and time in the coming years, will catalogue billions of galaxies and provide new constraints on the distribution of matter and dark matter across enormous volumes of space. What these instruments will find we do not yet know. That is the nature of genuine scientific frontier work. Predictions can be made, hypotheses formulated, expected improvements in precision estimated. But the history of astronomy is full of moments where new instruments revealed not confirmation of existing models, but surprises that required those models to be revised. The James Webb Space Telescope found massive galaxies in the early universe where few were expected. Future surveys of the Great Attractor region may find structures or mass concentrations that the current velocity data did not predict, or may resolve the existing tension between different estimates of the attractor's mass in ways that shift the overall picture significantly. The story is not finished. It is not even close to finished. And that is, when you think about it, the most exciting thing of all. We are living in a moment in the history of human knowledge when the tools to understand the large-scale structure of the universe are advancing rapidly, when each decade brings instruments powerful enough to see things the previous decade could only guess at, when the map of our cosmic neighbourhood is being redrawn in real time by scientists working at observatories around the world and in space above our heads. The Great Attractor will be better understood in 20 years than it is tonight, and better still in 50 years. And the picture that eventually emerges may be stranger and more remarkable than anything we currently imagine. The uncertainty is not a gap in our knowledge. It is an invitation, an open door into a room that is still being furnished, in a house that is still being built, on a cosmic scale that will take generations of curious minds to fully explore. We have travelled a long way tonight. We began in the quiet of your room, with the simple observation that something is happening to you right now that you cannot feel and were never told about. We traced the history of its discovery, the patient and contentious work of scientists who noticed that galaxies were not moving the way they should, who mapped the flows and inferred the source and gave it a name that carried its own gravity. We explored what is being pulled, the vast and ancient structure of the Milky Way with its 400 billion suns. We followed the river of Laniakea to its gravitational heart. We peered behind the curtain of the zone of avoidance. We tried to see the attractor itself, partially visible, still mysterious, enormous beyond any human scale. We felt the speed of the fall and the silence that accompanies it. And now, in this final chapter, I want to set all of that aside for a moment and simply sit with what it means, not the science, the meaning, the thing that is left after the numbers quiet down and the only sound is your own breathing in the dark. Every person who has ever lived on this planet was aboard the same vessel. Not metaphorically, literally. Every human being who drew breath on Earth, from the first Homo sapiens who looked up at an African sky 100,000 years ago and felt something stir in their chest at the sight of the stars, to every person alive right now in every city and village and wilderness on Earth tonight, All of them have been passengers on the same journey, falling through the dark toward the great attractor at 1,400,000 miles per hour, carried along in the flow of Laniakea, embedded in the cosmic web, part of a gravitational story that was already ancient before the first human footprint was pressed into the first patch of soft earth. We did not choose this journey, we were born into it, every single one of us, without exception, without awareness, without any sensation of the motion at all. There is a kind of profound solidarity in that fact, if you let it land properly. Every division that human beings have ever drawn between themselves, every border and boundary and category and conflict, every reason that has ever been invented to see another person as fundamentally separate from oneself, all of it has been happening aboard the same galaxy, in the same gravitational current, falling toward the same invisible destination at the same speed. The divisions are real in the sense that human experience is real, and I do not want to minimize the weight of that experience by dissolving it too quickly into cosmic abstraction. But the shared journey is also real, in a physical and literal sense that no philosophy or ideology can alter. We are all on the same ship. We have always been on the same ship. The ship is a galaxy, and it is falling through the dark, and it will continue doing so long after every one of us has returned our borrowed atoms to the universe that lent them to us. Think about what those atoms are. Every atom in your body was forged in the interior of a star that lived and died before the sun was born. The carbon in your cells, the oxygen in your lungs, the iron in your blood, none of it was created on Earth. It was created in stellar furnaces across billions of years of cosmic history, scattered into space by stellar explosions, gathered into the cloud that collapsed to form our solar system, incorporated into the Earth, cycled through oceans and atmospheres, and living things across 4.5 billion years of planetary history, and eventually assembled, briefly and improbably, into the particular configuration that is you, lying here tonight, thinking about where you're going. You are made of the universe, not as a poetic sentiment, but as a statement of physical fact. Every atom of you has been part of this journey for far longer than you have been alive to notice it. Here is the thing most people do not realize when they truly absorb this picture. The Great Attractor is not something out there that is happening to us. We are part of it. Our galaxy is one of the 100,000 galaxies of Laniakea flowing toward the attractor basin. The matter that makes up Earth, the matter that makes up your body, is part of the gravitational flow. The attractor pulls on every atom of you with the same or ancient, patient force it applies to the stars and the gas clouds and the dark matter halos of the Milky Way. You are not watching the universe fall toward the Great Attractor from a safe and separate distance. You are in the fall. You are the fall in the same sense that a single drop of water is part of a river, not separate from the current, but constituted by it, shaped by it, carried by it, and ultimately inseparable from it. We are the universe noticing itself. This is a phrase that has been spoken in various forms by various thinkers across the history of science and philosophy, and it sounds abstract until you apply it to something concrete like the Great Attractor. The universe has been falling toward this gravitational basin for billions of years, in complete darkness and complete silence, with no awareness of itself or its motion or the structures it was building. And then at some point in the last few 100,000 years, on a small rocky planet in a quiet arm of a middling galaxy in a supercluster of 100,000 galaxies, matter organized itself into a form capable of awareness, capable of curiosity, capable of building instruments and conducting surveys and tracing velocity flows across 500 million light years and inferring the existence of an enormous, invisible gravitational concentration from the behavior of the matter surrounding it. The universe, through us, discovered the Great Attractor. The fall became aware of itself, And in that awareness, however brief and fragile, something genuinely new entered the cosmos. That awareness is what you have been exercising tonight. The particular quality of attention required to follow the story of the great attractor, to hold the scales in mind, to feel the speed and the silence and the age of the pull, is a form of participation in the universe's ongoing project of self-understanding. You are not a passive audience for this story. You are one of the places where the story becomes conscious of itself. And the next time you step outside on a clear night and look up at the stars, I hope you feel that double awareness, the smallness of the body standing on the small planet under the enormous sky, and the largeness of the mind that can reach across 250 million light years and feel the pull of something it will never see and never reach and never stop falling toward. Thank you for joining me tonight and for staying with me through the full depth of this journey. If this exploration moved something in you, if it left you looking at the night sky differently, please take a moment to like the video or subscribe to this channel. It is a small action, but it helps this channel reach more curious minds, more people willing to lie in the dark and think about where they are and what they're part of. We are all falling through the dark together, every one of us, aboard this ancient and beautiful and terrifying galaxy, toward a destination we will never reach, on a journey that has no end we will live to see. And that is not a tragedy. That is the shape of existence at the largest scale we know how to measure. Sleep well tonight. Let the pull carry you gently into whatever dreams are waiting. And the next time you look up at the night sky and feel that old familiar pull of wonder, know that it is real and that it goes all the way down and all the way out and that you are part of it. Good night.